Okay, so let's get started here. So we'll talk about project number 2 shortly. Project number 3 we will discuss at the end of class today. Are there any questions before we get going? Okay, so first of all, just briefly mention I'm actually using a different computer today. I recently purchased one of the new Microsoft Surface 2 Pros, and hopefully everything will work out. This is the first time I've used it for teaching. It's kind of an interesting computer. Perhaps some of you have seen at least the TV commercials for them. You know, it's basically a small laptop or a kind of a bulky tablet. But the key thing is that it's a tablet, but it also has Windows, the full version of Windows on it, which is what I would need for teaching purposes. So we'll see how things go. Also with this new computer, then I decided to install the newest version of TIN, so you're going to see me use a different version of TIN than what I normally do in class. Okay. So let's briefly talk about project number 2. So hopefully all of you have taken the time to read my listserv posting about it. As I said, that overall the grades were decent, and I did indicate a few places for you to take a look at there. But I do want to say something else that I did not actually put up there, and that is please be very careful with your writing. I'm talking to both the native English speakers and the non-native English speakers. Most of you do a very good job, but there is a significant number of you who do not, to be brutally honest. Misspellings, starting a sentence with a lowercase letter. Well, what are some other ones? Words that just don't make sense where they're put, and just overall sentences that make no sense at all. Now, the reason why I bring this up now, and I have taken off some points, not a whole lot, but I have taken off some points in the past. The reason why I bring this up now is because when you graduate from here, you're going to have problems when you're at a job, because your supervisors are going to read what you write, and they're going to have problems understanding you if you do the same level of writing and the job as you are doing. Let's say some of you, not all, some of you for this particular class. In fact, you might even have problems finding a job if they see your level of writing or texting in other cases too. But anyway, I just want to bring that up. If you need help with your writing, there is help available on campus. There's what's called a UNL Writing Center. They have people there that will help you. It's put together by the English department. I recommend that if I've indicated to some of you that there are problems with your writing, I recommend that you go talk to them and see if they can help you. Okay. Hold on. Let me change some of my power options here so that the screen doesn't go blank. Let me actually try that. We'll test to see if Surface 2 Pro does indeed have more battery life. Anyway, so that's all I have to say about the project. Are there any questions? Yes.
Yes. What's the main reason of not adding a new applicant to the entire data set before running the analysis?
Well, it's a new applicant, and so you've already, let's say, run your analysis, and now you want to see, well, where does this person fit in with what you had previously? I've indicated this before in class. You leave the applicant out. And another reason why to do that is to get to the final part of that problem number 1, and that is, well, of the applicants that did, let's say, apply on time, which ones are the best? And so that's essentially that's the main purpose of this perfect applicant, because then you can see where that applicant, you can see where the perfect applicant would fall, and then you can judge based upon the actual applicants which one would be best. Because if you put that new applicant then in the data set and reran the analysis, well, then now you're changing everything. well, to some respect, you're changing the factors, the factor loadings, for example, because now you have a different data set. Does that make sense? Okay. Other questions? Okay. Let's see. So we're talking about discriminant analysis. And the purpose of discriminant analysis is to basically predict the correct population that an observation came from, or you could say equivalently the correct classification. As I mentioned to you last time, I'm going to use often different terminology because outside of this class you're going to find people use different terminology. So I'm going to maybe call it population sometimes, I might call it classification another time, I might call it grouping another time. So we want to be able to predict the correct classification. In the context of the place-kicking data set, that means that we have a success population, we have a failure population, and given certain characteristics about a place kick, such as the distance, such as was there pressure or not, such as is it windy or not, we want to be able to predict, is this place kick going to be a success or a failure? Now, as you might imagine, that these methods that we have here, these discriminant analysis methods, are not going to be perfect. They're not always going to result in a perfect, classify all, let's say, the successes as successes and classify all the failures as failures. And so because of that, we want to look at ways that we can gauge how good a particular statistical method, or what we'll also call a discriminant rule, is in classifying these observations. Last time I mentioned that there are 4 different ways to gauge how accurate a particular discriminant rule is. We looked at the first 2. Let's just review those briefly. The first one is to collect new data. So let's say that you have a data set, you develop your discriminant analysis method upon it, that gives you a discriminant rule that says classify into this population if something happens, classify into this population if something else happens. Okay? Now to try this rule out, to see how it would actually perform in application, well, why don't you go out and collect some new data and try this rule on this new data, see how accurate it is. This is the best overall method in terms of estimating the classification accuracy. The problem with it is that when you have to go out and collect new data, of course it's going to take time. It's going to probably cost you more money. So an alternative then is to use what's called a holdout data set. And you can do this as long as you have a large enough original sample size. What this says basically, and actually I do this with the place-kicking data set. With the place-kicking data set, I collected information, I think, on 1,700 place kicks. And what I did was, once I got that data, I removed 20% of the observations from my data set, put it aside, then performed discriminant analysis on the remaining 80% of my observations. Once I got done performing the discriminant analysis on those 80% observations, I came up with a discriminant rule, a classification rule. And I use this classification rule then on this 20% of the data that I put aside to test it out, see how it would work. Okay, so this holdout data set, sometimes you'll see it referred to as a validation data set. Some people call it a calibration data set as well. The original data set in this, I guess, case number 2 here is often called the model building data set or the training data set by a variety of different people. Okay. So then the third way to go about doing this is to use what's called resubstitution. This is the worst method. Again, this is the worst method. It's the most intuitive method, but it is the worst method. There are situations where this might be the only thing that you're left with, that this is all you can do. What resubstitution basically says is, well, you got a data set. Maybe you have 100 observations, let's say. Develop your discriminant analysis method on those 100 observations, and then simply on those 100 observations, apply the discriminant analysis method to each observation to see how well it does. The problem with this is that your method that you develop, your discriminant rule that you develop, is going to perform the best in this situation because you have developed the method on that same exact data set. Okay? So in the end, your classification accuracy measures that we're going to look at in terms of I classify my observations 80% of the time correctly. That classification accuracy measure that you get from applying resubstitution will be biased. Okay? Generally speaking, bias is not good. It's going to be bias high, in fact, I should say. So, you might get 80% correct classifications as suggested by resubstitution, when in fact maybe one of those other methods might say 70%. That's what I mean by biased high. So what is most often then done, I think pretty much I would do this every time that I do a discriminant analysis. I do this every time that I do a discriminant analysis, except for if one little thing happens, I don't. And that is to use what's called cross-validation. If any of you have heard of a particular statistical method called jackknifing, this is jackknifing. And this is how it works. So let's say maybe you have a data set of 100 observations. Take the first observation out of your data set, develop your discriminant analysis rule based upon the remaining 99 observations, and now apply this discriminant analysis rule that you got on this observation that you took out. Apply it so that you determine, is it, let's say, population 1 or population number 2 predicted, and compare it to what was actually observed. Now put observation number 1 back in the data set, but now remove observation number 2. Come up with a discriminant analysis method on the remaining 99 observations. Apply it to this observation number 2 that you had removed, and look at how well it does. Does it predict the population classification correctly or not? And you do this for all 100 observations. While this does not necessarily give you an unbiased estimate, but it gives you something that's rather close to being unbiased. It's much better than the resubstitution method. So what do you think a problem will be then applying this particular method? What could be a problem? Yeah, but you're not supposed to look at those additional notes. But yes, I know. Sometimes I wonder if I should just take out all my comments, or maybe I need to. These are the comments that you see there, as I mentioned before. They're for my purposes, and I'm hoping, because when you print them off, it really makes your stuff that you print off smaller. But anyway, I understand.
It was quiet, so I just said it. Sorry.
Well, thank you. You did break the silence. Anyway, so computationally intensive. So what that basically means is, all of you have heard the phrase over the last couple of years, big data. That means, let's say, 1 million, 10 million, 100 million, 1 billion observations. It's not unheard of nowadays. Imagine applying this cross-validation to a data set that has 1 billion observations. How many different discriminant analysis rules are you going to find? 1 billion plus 1, because you're removing each observation one at a time. And then you have overall, for all billion observations, you have one overall discriminant analysis method that you would apply, let's say, to a new data set or new data that you might have down the line. So you can see that this could be computationally intensive. It could take a long time to do. Yes?
I have a question about this. We do something like this with our genomic selection models where we're looking at prediction accuracy.
Okay.
And the way we do it is to select a percentage of the observations that we leave out and then validate against. And we iterate through randomly selecting that fraction.
So if I understand you right, let's say you have a data set of size 100, and you might remove 10 observations, apply it to the next 90. Right. Put the 10 back in, take another 10 out. Okay. Yeah, that's just another form of jackknifing.
So do people do that with discriminant analysis?
I have not seen it done in a discriminant analysis case. Perhaps I shouldn't say this because I cannot remember the exact place where I've seen this, but I don't think that there's really much benefit from doing what's called, what would be the word? I'll just use the letter K, the K leave out procedure, which is where K is equal to 10, let's say. I don't see a benefit from doing that versus doing it this way.
And it's in computationally less intensive.
Yeah, I guess that would be one. Yeah, that would be one situation where it would be computationally less intensive, depending upon what you're actually doing. So I guess that would be one advantage. Perhaps you're doing some computationally intensive stuff, and so that's why it makes sense to do that. But if it didn't, if the actual statistical procedure that you're applying to, let's say, the remaining observations, if that is not taking a whole lot of time, I don't see a benefit from doing a leave K out versus a leave 1 out. But it is jackknife. It's one of those few interesting names that we have in statistics. The jackknife. It was came up someone by the name of John Tukey, who's a very famous statistician, came up with that name. Okay. So, again, if given the choice between resubstitution and cross-validation, generally speaking, always pick cross-validation. The only time that resubstitution might be better is if you do have, let's say, a big data set and the computational time is too much, and so you're left with resubstitution. Okay. So let's talk about the place-kicking data set, apply some of these discriminant analysis methods that we looked at last time to it, and then also evaluate how well our methods do with respect to these classification accuracy methods, you could say, that we just talked about. Okay. So our goal here is to develop what's called a discriminant rule, or a classification method, again, just to use different terminology, to determine which places are going to be successes and which are going to be failures. To help us do this, in order to measure how well our method is, I should say, we're going to use, you could say, the methods 2, 3, and 4 of how we can measure classification accuracy. So the only thing I'm not doing is collecting new data. As I mentioned, I actually collected data, about 1,700 observations, and once I got done with data collection, I removed 20% of the observations randomly from my data set, put them aside, and then tried to come up with a discriminant rule, first of all, based upon the 1,400 observations or so, or the 80% of the observations that were left. Unfortunately, I lost my train of thought there, what I was going to say next. Let's just make sure we are still recording. Good. No, I'm sure I'll think of it eventually. So let's take a look at the data set. So it's in placekick.csv, with the limited file. These are the first 6 observations. Then my holdout data, validation data, calibration data is in a file called valid.csv. You see the first 6 observations there. So hopefully you remember from last time that these discriminant analysis methods basically say either X is distributed multivariate normal with mean mu1 and covariance matrix sigma 1, or X is distributed multivariate normal with mean mu2 and covariance matrix sigma 2. What do you think about multivariate normal with this data? Do you think the data is going to satisfy multivariate normality?
No.
No. Why?
Because a lot of these variables are categorical.
Exactly. So a lot of these variables are categorical. So right away, you can see that we are violating some of the underlying assumptions of our discriminant analysis. Hopefully also you remember from last time I said, even if we do violate these assumptions, these discriminant analysis methods tend to still perform okay. We will look at other methods that we could use that do not have that multivariate normality assumption with respect, and then we can apply to this data set. We will look at those as we go throughout the remaining of the semester. Let's take some time to review what these variables actually represent. So we have and this is actually in the data distributions and correlation section. It's actually outlined there. So we have the week variable, which represents the week of the season that the place kick took place. The distance of the place kick in yards. A change variable, and what this represents is basically a measurement of pressure. So for example, let's say, let me bring out my pen here. Let's say the score was 7-10. Make that a little bit less thick. And the team with 7 points is trying to kick a field goal. If successful, 3 points will be added to the 7. So now the score is 10-10, and this represents a lead change. So instead of the team that was on the right-hand side there, you could say leading, now the game is tied. If instead the score was 8-10, and the team with 8 points was attempting a field goal, and if successful, it will be 11-10, then this is called a lead change place kick. In this case, the change variable will be equal to a 1. If the score was instead 6-10, with the team with 6 points kicking a field goal, if successful, the score will be 9-10. Notice there's not a lead change at all, so this is change will be equal to 0. Okay. A lap 30 corresponds to the number of minutes remaining to go in the half. There's 30 minutes and a half. So, for example, with the first observations, there was 24.7 minutes left to go in the half when that place kick was attempted. There are 2 different kinds of place kicks in football. There's what's called a point after touchdown, which is worth 1 point if successful. There's also a field goal, which is worth 3 points if successful. So PAT equal 1 corresponds to a PAT. A PAT equals 0 corresponds to a field goal. The type variable, let me just make sure I get this right. It corresponds to the type of stadium that the attempt is done in. 0 for dome, 1 for inside. Field is the type of surface that they're playing on. 1 for grass, 0 for artificial turf. Wind is equal to 0 for not windy, and 1 for windy, where I use 15 miles per hour as the cutoff for windy versus not windy. For those of you who did not take my SAT 875 course, why do you think I needed to make this a binary variable instead of just using the actual wind speed? So you might think, okay, why don't I just put the wind speed there for the wind, but instead I made it binary, 1 for windy, 0 for not windy. Sorry, I don't think the answer's in the notes. The reason why I had to do this was, and there's not a perfect solution to this problem, is what's the wind speed inside of a dome stadium? Is it 0? There's air circulation going on there. For example, in Detroit, for the dome stadium, the Pontiac Silverdome that they played in at the time, the Detroit Lions, I would always get a wind speed in there about 1 or 2 miles per hour. Okay, it's not 0. If any of you follow baseball, in particular Minnesota, and you heard of the Minnesota Twins when they played inside a dome stadium, there's always been a legend that, let's say, when the other team comes up to bat, the people who run the Metrodome would turn up the air conditioner, and the air from the air conditioner would hopefully help blow a baseball when it's hit, keep it in play versus allow it to be a home run. So there is air circulation in a dome stadium, and what do? Do you assume it's 0? Maybe that might be one solution. I thought a better solution would be, well, is it windy versus not windy? And so that's what I did. And I should mention that only Detroit gave me information about wind speed. The other dome stadiums did not, so that's what concerned me. So anyway, if you have a problem with it, no, sorry, the paper's been published. You can write an article, a reader reaction paper to it if you really want to. And then lastly, the good variable is what you can think of as our response variable. You can think of it as denoting the different types, different populations, or the different classifications, the different groupings. 1 for a successful place kick, 0 for a failed place kick. Okay? Any questions about the data? Also, I guess I should mention too, another problem that I had with wind was obviously the wind direction is very important too. There was a number of problems with it. Some of these correspond to more so when I collected the data. And that is while I did have information on wind direction, my problem at the time was the stadium orientation. Well, most stadiums are oriented north-south. Well, it might be northwest to southeast maybe instead. Or, you know, I know at least in college football, for example, Oklahoma State's football stadium is oriented east-west. And so I had problems finding the stadium orientation because there wasn't something called Google Maps back then when I collected this data back in 1995, 1996. So obviously that problem can be solved nowadays. But another problem is that wind tends to swirl in stadiums. So even though the wind might be out, let's say out of the north at 10 miles per hour, once the wind hits the stadium, the wind can swirl. And so you might have, I'm sure all of you were watching the Nebraska-Michigan game this weekend, and you might have heard the announcers talking about how the wind is swirling in Michigan Stadium at the time. And that was explaining perhaps why some kicks were being longer than others. So anyway, a lot of interesting problems with that. And that's what happens with real data. Okay, so when you get a data set like this, one of the first things that you should do is do some initial investigations, do some exploratory data analysis. Well, guess what? That's what we spent a lot of the course so far on. And so what we can do is apply the stuff that we learned in the graphics section. Also, what we can do is apply some of the, let's say, principal component analysis stuff that we did so that we can get an initial understanding of the data and form an initial interpretation of, do I think I'm going to be able to discriminate between the success and the failures? Meaning, will I be able to come up with a classification method that will allow me to differentiate between the two different populations? So, what I chose to do to show you only here, just to save time, is the principal component analysis. So let's see what happens. So I apply principal component analysis much as we have done before. So I put all the variables except for the good variable in here. Because when I show you some principal component score plots, I'm going to let the plotting point correspond to the good variable. Because, again, what we're interested in is seeing, can I differentiate between the two populations using the other variables? Okay. So here are my, here's my output here. How many principal components do you think would be good to use? Five. Well, we have 5 to 80, gets you above 80%. Also, you could look at, well, the number of principal components that are greater than or equal to 1. I'm sorry, the corresponding eigenvalues. That will give you to 4 principal components. But remember, as we discussed before, you could still, let's say, maybe just look at 2 or 3 so you can get, let's say, the best 2-dimensional representation of your data, the best 3-dimensional representation of your data, and just understand, have in the back of your mind that you're not seeing the whole picture, but you would think that if you looked at the data in 2 or 3 dimensions and something's coming out to you that shows that, yeah, I can see the differences between the two populations, well, that's going to hold true for 4, 5, 6 dimensions too. And so again, what you're trying to do is explore the data, get an initial interpretation of it, and there's nothing wrong with only looking at 2 or 3 principal components.
I have a question about that.
Sure.
So if you can easily look at more, what's the point in looking at?
The problem is this. The easiest plots, hopefully that you've seen this, the easiest plots to interpret are the scatter plots. Okay? While you can do like parallel coordinate plots, they are more difficult to interpret. So that's why. Actually, it would be typically good to do both in this situation. I'm only going to show you the scatter plots, but it would be typically good to do both. So I exclude the plotting code because we've done these kinds of plots a lot before. And here is a plot of the first two principal components. So what I've done is I color-coded the successes and the failures. And so what do we see from looking at this plot? Again, focus your attention on do you think that we will be able to develop a statistical method that can differentiate between the two populations? Not necessarily perfectly, but do you think we can maybe have some success? Excuse me? PC what? PC number 1, what about PC number 1? Is more? Or smaller? Yeah. Notice as PC number 1 gets smaller, you see more of the black plotting points. So that then tells me, okay, something's going on here. There is some differences between the two populations. Obviously, we see big overlaps between the two populations. The reds and the blacks still mix. But I'm thinking that maybe I might be able to do something, have some success, not necessarily perfect, but some success. Now, what you should do, too, is in the back of your mind, think about, well, what would this plot look like if you think you're going to be 100% successful? Well, let me just ask you, what do you think this plot will look like if I think I'm going to be 100% successful?
2 clusters.
2 clusters, I think what you're getting at, all the blacks, let's say, would be on one side, all the reds would be on another side. Okay? And the more overlap you see, the less successful that you're probably going to be. So that's what we're looking at with these kinds of plots, again, to get an initial interpretation of our data. Okay. So we can also do some 3D plots as well. I've already done one here. So again, take a look at where the red and the black fall. Notice, especially down below, you start seeing some separation. If you follow where my mouse is, you see some separation down here for where the blacks are. So this third principal component is telling us something that, maybe some of these smaller PC number 3 values that have a corresponding PC number 2 and a corresponding PC number 1 should maybe always be classified as failures. And again, this is saying to me that, yeah, I might have some success with differentiating between the two populations. Also, you should notice here in this plot, there's a number of things to notice. Obviously, we have a lot more reds than we have blacks. In fact, I think we have about 88% successes, about 12% failures. Okay, that's going to play an important role for us coming up, and I'll talk about that more. Okay. Now, also, you've probably been wondering, well, you have these bands of points. Where do these come from? Well, you typically see bands of points such as this when we have discrete data. So, you saw, for example, the change variable, 0 or 1, the PAT variable, 0 or 1. And just to illustrate the effect of having these discrete variables, I changed the color of the plotting point to correspond to one of these discrete variables. So you can see the PATs are in blue, the green are the field goals. And you can see that, well, this is what's somewhat separating the observations into these different bands. For those of you who are football fans, look at where the blues are, correspond to where you see a lot of the reds are. If you're a football fan, you know that PATs are most likely always going to be successful. And so that's why you see all these reds on this side of the plot. I did one other example. So this is the, let's see now, grass versus artificial turf. So grass ends up being on top and artificial turf is on the bottom, again, of those bands. And, all you need to do is take a look at the principal components, look at the actual equations, see what happens when you put, let's say, 1 in for grass, or I'm sorry, 1 in for the surface or a 0 in for the surface, and you can see why this banding occurs. Okay. So the function that we're going to use now in R, so right now we've concluded that, yeah, it looks like we might be able to have some successes. Probably not going to come up with something that's perfect, but we probably will have some successes in our classifications. So now we can apply the discriminant analysis method. The function that we're going to use first to do this is called LDA. DA obviously stands for discriminant analysis. The L stands for linear. Where that name of that part comes from is the fact that if you remember, we looked at 4 different ways to make a decision of is the observation population number 1 or population number 2. The second way was what's called the linear discriminant rule. And it basically had this form here. B prime x minus k, where b and k are constants based upon mu and sigma. You can go back to the notes to take a look at that. And so what you can see here, what we're doing is x is our data, and what we're doing is simply finding a linear combination of our data, b prime times x. So that's why this is called linear discriminant analysis, or LDA for short. Later in these notes, we're going to look at something called quadratic discriminant analysis, or QDA. There's going to be a function called QDA that will allow us to apply it. And in that case, we will take a quadratic form of our x's. More on that later. Okay. So the LDA function comes from the mass package. We've looked at the mass package before. This function is written by someone by the name of Brian Ripley. And this is how the function works. I'm going to put the results into an object called DA1, for the lack of a better name. And then formula equal, you put in you can say your independent, you put in, use kind of a modeling format like you do with like the LM function, if you remember that, where we have on the left-hand side, we have like the response variable, in this case good, because it tells us what the populations are. And the right-hand side of a tilde, we have the corresponding variables that we're using to try to differentiate between the two populations. You put in your data set name, and then we have an argument called CV. What do you think CV stands for? Coefficient of variation? No. Cross-validation? Yes. Okay. So CV equal false. For illustration purposes, I'm going to first do this with resubstitution. Okay? So that's why I decided to do CV equal false. But let me emphasize that most often we don't want to use resubstitution. It's helpful for illustration purposes to do it this way. And then we have something called prior. I'll explain more what this means later on. But what this basically corresponds to is I'm assuming here, if you notice, basically I have a vector that has 1 over 2 or 0.5 in 2 different places. Basically what I'm saying here is 50% of my observations should be successes, 50% should be failures. Now we know that wasn't what was observed. Okay? But again, for illustration purposes, I'm using this at this moment. We'll talk more about the prior argument later on. But it's going to be helpful for me to demonstrate some of this stuff without the LDA function. Okay. So here's the output. And actually, you know, this output's not really too useful. I do want to point out, though, what this group means gives us. So what this says is that for each of the different populations with the different success or failure possibilities, what is the mean value for a particular variable? So you notice, for example, with the distance variable, the mean value for the failed place kicks was 40 yards. For the successful place kicks, about 26 yards. Notice here for the change variable as well. Change is equal to about 0.4 for the failed place kicks, 0.23 for the successful place kicks. When you see separations like that, that makes you think, okay, maybe I could differentiate between the two different populations. because we can see that one population has, let's say, maybe a higher mean values for some variables, and another population has a lower mean value for some variables, seeing that there are differences. It doesn't say that they are completely separated, the two populations, it just says that there are some differences. Okay. Do I want to talk about that now? No, I do not. I'm going to skip that for now. So what information then is given to us inside of DA1? Well, just similar to what we've done before, I use the names argument, and we see some information that's given to us. Yeah?
Yes, for the mean, they calculate the mean within each
Population.
population. Like for change, they calculate the mean for change 1 and change 0, or?
Yeah, that's why they're listed separately.
And you couldn't have categorical response either.
This means that this, well, in the, if you look at the data set, well, let's actually do that. Okay, let me do this instead. So let's look at the change variable. So you can see there's all the zeros and ones. And what I'm going to do, we'll use the table function. If you remember the table function from 875, we can simply look at a contingency table summarizing the responses. Place kick $sign, good. Let's see, change. So here what we have is simply 95 times. I believe that these are the failures versus successes. 95 times we have a change equals 0 when the good variable is 0. 68 times we have a place kick that is, let me actually do it in different ways so I know exactly what those are saying. So we can use the xtabs function as well that you learned about in 875. Let's see here. There we go. Now we have the labels. Okay, so given it's a good, why don't you average these values in terms of you have 95 zeros, you have 68 ones. Take the average of 95 zeros and 68 ones, and you will get 0.23. Or, I'm sorry, you get 0.41. Does that make sense? Are you sure?
You average 95 plus 65.
No. I have 95 zeros. I have 68 ones. Take an average of all those zeros and ones. Sorry if that wasn't clear. Okay? That's where that's coming from. Are there any other questions? Okay. Let's see here. Now, really the main thing that's of interest to us from getting the information from LDA is actually using with LDA the predict function. We've seen the predict function before. For example, with a regression model, we can then come up with the predicted Y values, let's say. Well, here what we're going to do is come up with the predicted classifications. And so we say with predict, object equal DA1, put the results in an object called pred.resub. So I'm actually using resubstitution to do this prediction. What comes back then is that one component is the posterior probabilities. Remember those from last time. So for example, observation number 1 has a posterior probability of being in the failed population of 0.11. Observation number 1 has a posterior probability of being in the successful population of 0.89. So should we classify this as a success or a failure? Success, because the probability is higher. That's simply how it works. Okay. And also inside the pred.resub object, there's something called class. This is the actual classification then for us, based upon using a 0.5 cutoff, essentially. So that's why you see for the first observation, that's why you see a 1 there. Classified as a success. So note that R does not give us the Mahalanobis distances, but essentially uses the Mahalanobis distances to calculate these posterior probabilities. Something else that R does not give us, which I find interesting, I haven't seen this before in a software package, it doesn't give you this B prime X minus K. It does not give that information to you. At first, when I was going through this, I thought it was doing that, because we see something called coefficients of linear determinants. And typically in the output that you see in other software packages, you will see B, that B for B prime X, you will see that B calculation given to you in the output. SAS does it, for example, in Proc-Discrim. And then you also see in the output K as well, automatically calculated for you. And so when I saw this, I thought, okay, this has something to do with this B vector. And instead, and this is talked about on page 18, instead, Brian Ripley does something that's kind of different. What he decides to do is that he basically gives you what you can say is a rescaled version of this B vector. And I decided that after reading through what's done and taking a look at Ripley's actual book, textbook on this kind of stuff, I decided it just wasn't worth our time to understand why he's doing the rescaling. He says he's doing it for computational reasons, because although I've never really had any problems before with discriminant analysis using the straightforward method. And so I guess the big picture, though, I don't think it's worthwhile for us to see what he's exactly doing with that stuff in the outputs. I will show you very shortly how you can calculate that B vector without using the LDA function. Okay, so now it's nice that we have this LDA function that does most of the calculations for us, but since this is obviously a master's level stat course, you need to know how these matrix calculations are actually done without using the LDA function directly. So that's the purpose of this next discussion. Okay, so the first thing I'm going to do is get a vector of my data that has just observation number 1 in it and show you how resubstitution is used for it. So I pull out observation number 1 from my place-hick data set. I had to use the as.matrix function to make sure that R recognizes this as basically a vector, a mathematical vector, that is. In this particular case, it is an 8x1 mathematical vector. So essentially this would be in our notation then our x. Okay? And I want to classify this x. Before I get to that, though, I need to do some other calculations. So I need to pull out of my place-kick data set all those observations that correspond to failures. I'm going to put that into an object called pop0. And then all the place-kicks that correspond to successes, I'm going to put that in an object called pop1. Are there any questions about, so I think we've done this now a few times, perhaps I'm wrong. Is there any questions about what that does? Okay, silence means that there's no questions, and I'm going to move on. Are there any questions? Okay, the -9 corresponds to, I don't want the good variable in my data set. In the 9th column, sorry, I didn't mention this, the 9th column is the good variable. So are there any questions about what I circled up there?
Can you explain it?
Susie? Sure. Thank you for asking. Okay. So a common way in R to extract certain parts of a data set is to basically come up with true or false conditions for the rows of a data set. So when I say place kick $good equals 0, I need to have both equals there. What that does is it does a logical check. For every single observation in the data set, the good values, is it equal to 0 or not? So if I just highlight that segment of code and hit run, you see a whole bunch of trues and falses. So for example, the first observation in the data set is a false. I'm sorry, the first observation in the data set is a success. Okay? So combining all these trues and falses then, and the row, for a row number, essentially, we've looked at how we've been able to extract rows before. If I put a 1 there, that means I'm going to get row 1 out. If I put a, let's say, 1:2, that means I'm going to get rows 1 and 2 out. By combining all those trues and falses then in that part of that code that says all the observations that have a true associated with it, I'm going to pull those out of my data set. So that in the end, if I run this here, and let's do a head on pop 0, these end up being all my failures in the data set. How many failures do I have? That's where I can do n row, pop 0. There were 163 failures. Any questions? Anybody else like me to demonstrate what that does further? Okay. Let's see here. So now I find the number of observations that I have using the n row. I find the covariance matrices for each of the populations, or estimated covariance matrices for each of the populations, just like what we did in the data and distributions and correlation section. I find my pooled estimate of the covariance matrix. If you remember us doing that last time. I also then find the mu hat, the mean vectors for each of the populations, call them mu.hat0 and mu.hat1, using the call means function that we've used in the past. I also had to use as.matrix with it to make sure that R recognizes this as what we think of as a mathematical vector. Next, what I do is I simply find my B and my K for the linear discriminant rule. And just to review that, let me do a split screen here. I'm going to go, this is a little out of order, but I think we can still do this. Okay, so on the bottom here, you're going to see my B prime X minus K. In the top there, you see my actual code. So what I need to basically do for B here, I need to find the inverse of my covariance matrix. So that's what I'm doing here. Oh, come on, pen, work for me. So there's the inverse of my covariance matrix. And then I take it times, then, the difference of the two main vectors. So my notation down here, I had labeled them mu1 and mu2. So essentially 1 is population 0 for me, 2 is population 1 for me in the place kicking data set. So I just transformed this, these mathematical calculations into an R syntax. I do a very similar thing then to find my K value. And so with that, here's what my B vector is. This is what my K is. And so in order to make a decision about, well, which population does observation number 1 go in, I take the transpose of B times my X, so B prime X. I subtract off K, and I get a negative 2.09 value. So let me go back, make that bigger again. So if b prime minus x is greater than 0, I choose population 1. Otherwise, I choose population 2. So which population am I going to choose here? Population 2. And that, for us, in the place-kicking data set, corresponds to the successes. Okay. So that's how the linear discriminant rule works. I can also find my Mahalanobis distances as well. So if you remember how that works, we take x minus, I'll do for 0. X minus is mu 0, so the estimated mean vector for population 0, the failures, take it times, or transpose it, take it times the estimated covariance matrix inverted, and then again apply x minus mu hat 0 to that. And so we're essentially looking at, well, how far is x from the center of the failures, if we think of the mean vector as the center. And that distance ends up being 17.55. We do the same thing for the distance to the successes. We get 13.37. So is the x closer to the failures or the successes? It's closer to the successes. So because of that, it seems to make sense. Why don't we just classify it as a success? And so that's how it works with Mahalanobis distance. And then lastly, using the posterior probabilities, and if you remember the formula, what it looked like was we do something like this. We take e raised to the negative 1/2 times a distance, how about if I just call it d, all over, how about we call that, we're going to do it to the distance of the failures, all over e to the negative 1/2, the distance to the failures, plus e to the negative 1/2, the distance to the successes. We calculate those probabilities. I put into the correct R syntax, and we do the calculation, and guess what? These probabilities are exactly the same as what the predict function gave us. So yay, R is doing the calculations correct. Any questions? Okay. Let's move on then. Well, let's say that we do want to do cross-validation. How do we do it? Well, simply change one part of my LDA code. I use CVA equal true. I'm going to put the results from the LDA into the DA2 object, for the lack of a better name. Now, unfortunately, Brian Ripley, the author of the LDA function, I don't think he added this option. I could be wrong. I don't think he added this option or this argument for CV until maybe a few years ago. And he doesn't, unfortunately, really put together a nice form for the outputs. And so because of that, he basically doesn't have the output printed nicely at all. If you were just to say DA2. I guess I can show it to you. Just to prove it to you that indeed the output's not very nice. So that's what the output looks like. He just has everything dumped to the screen that's inside of DA2. Don't complain to me, complain to him. So what's inside DA2 then? Well, you don't even need to use you can't actually use the predict function with DA2 itself. Instead, he has automatically all the posterior probabilities going into the object, DA2, along with the corresponding classifications. So if I say DA2 $ posterior, I have my posterior probabilities there. DA2 $ class, I have then the predicted classifications. Now you'll notice here, let's take a look at the first observation again. Here are the posterior probabilities. Previously with resubstitution, we had 0.11002 for the zero population. We have 0.88997 for the success populations. So you can see that they're quite close. Why do you think they're close? Because of the size of the data set. That's right. So to some respect, I told you, well, the one problem with cross-validation is that, if you have a very big data set, it might be hard to apply. But in the end, generally speaking, the results for cross-validation and resubstitution will be very, very similar with a large data set. Because think of the effect that cross-validation has. You're removing one observation at a time. Well, the larger your data set is, the less important that one observation is. Unless you have, if you've taken like a regression course, there are things called influential observations. Unless you had something that was very, very influential, and even with a very, very large data set, that can be difficult. The results are not going to change much. So now that we have these posterior probabilities, we have the classifications, let's look at how good does this discriminant analysis method do. And so to help you out to make that determination, I have written a function that you can use called summarize.class. Yes, I highly recommend that you use it. And summarize.class stands for summarize the classifications. Let's first look at how what the result of this function is, and then we'll go back and look at the code. So I say summarize.class, and I have two arguments. The original argument says put in there what the original observations, if their populations or their classifications, what they originally are in the data set. So the good variable in the place kick data set gives me my zeros and my ones, my failures and the successes. Then let's, for the second argument, put in the predicted classification. So I have classify equal, and I just pull out the class value of DA2. What's printed then is a list that has three components. There's something called class table, which shows me what observations were classified as successes and failures relative to what they are originally in the data set. So for example, in the data set, 124 of the failures are correctly classified as failures based upon this discriminant analysis method. But 39 of the failures in the data set are misclassified as successes. 274 of the successful place kicks are misclassified as failures. 988 of the successful place kicks are correctly classified as successes. So you can see we are having some success. What's often a little bit more helpful to look at is then the proportions of correct classifications. That's what's in the next set of information here. So 76% of the time, I get the failures correct with my classification method. In other words, this is 124 divided by 124 plus 39. 24% of the time, I get the failures wrong. 78% of the successful place kicks are correctly classified as successes. About 22% are not. So notice the row proportions add to 1. So essentially, if I guess you've heard this in 801, I'm basically finding conditional probabilities. Conditional in the row, what's the probability of the column? Then I do an overall correct percentage, 78%. How's that found? Simply I take 124 plus 988 over the sample size. I don't remember exactly what that was. I think it's like 1425. Or you can think of adding up all the counts in that first table. So 78% of the time I get it right. Not bad. Maybe both me wouldn't like that percentage, but that is still higher than his overall winning percentage, so he shouldn't complain. Anyway, So what about the resubstitution then? I do exactly the same thing, but now I use the pred.resub $class. And this is what I get. In fact, it is exactly the same. Why is it exactly the same? Well, we just got done talking about that with respect to observation number 1. Well, what about the validation data set then? Let's see how that works. So, how do I get then these observations to be classified in the validation data set? I use the predict function. Remember, this only works with if you were to use the LDA function with CV equal false. So even though we don't like resubstitution, we will always need to run the resubstitution way of doing LDA, the LDA function, if we have a holdout data set or validation data set or calibration data set. We will always need to. That's the only way we can automatically get these predictions done. And so we run it just like what we did before, but we add this additional argument. New data equal, put in your validation data set, put in your holdout data set. You put the results into pred.valid, for lack of a better name. And so we can see, for example, with the first observation, it would be classified as a success. The second observation would be classified as a failure. Then we can use my function summarize.class once again to summarize the classifications. And so now notice for the classify argument, I'm going to put pred.valid $class in there. And this is what I get. 75% or 76% of my successes are correctly classified. 79% of my failures are correctly classified for an overall success rate of 76%. So notice it's a little bit lower than what we had with cross-validation and resubstitution. It's typically to be expected. It won't always happen every single time, but typically it's expected. But then it's still giving me, overall, it's showing me I am having some successes with my classification. It's definitely not perfect, but I am having some successes. Okay, are there any questions? We went a little bit longer here than what I wanted to with respect to the notes. So what I'm going to ask you to do is on page 21 where you do see that summarize.class function, please look at that on your own, the contents of it. To understand exactly what's going inside of there, what you can do is simply copy and paste each line of the code outside of the function and run it one at a time to see what happens, where you've made the corresponding assignment for the original and the classify arguments. If you have questions about it, please bring them to our next class. But with the remaining about 5 minutes of class, let's take a look at project number 3 real quick. Okay, so similar format to as before. You can work in groups of up to 3 people. It's due Friday, November 22nd at noon. And it involves a data set that I briefly mentioned to you last time. It's this wheat kernel data set. And what we're trying to do is be able to correctly classify the wheat kernels as either being healthy, sprout, or scab. Okay? Excuse me. The data, you can download it from my course website. It's in the file wheat_all.csv. It's on the graded materials webpage. It contains 276 kernels. It contains information about the measurement of their density, hardness, size, weight, and moisture content. It also contains information about, was it soft red winter wheat or hard red winter wheat that this kernel came from. And then the ultimate goal is to be able to correctly classify using discriminant analysis, and also another method that we'll talk about maybe starting tomorrow, or Wednesday, correctly classify these observations as, again, healthy, sprout, or SCAP. So this is what the data set looks like. Okay. Again, the ultimate goal, and this is key, especially for number 1, develop methods that best differentiate between the kernel types using the physical characteristics of the kernel and the weak class. What I mean by that is soft red winter wheat or hard red winter wheat. Okay. So problem number 1. Similar to what I did with the place-kicking data set, I didn't necessarily do everything that I would normally do in the actual application with the place-kicking data set, but similar to what I was doing there, I want you to perform an initial investigation into this data. So where do you begin? You do some plots. So, you might think, for example, parallel coordinate plots would be very useful here. If you actually look at the data, you'll notice that basically all the variables except for one are essentially continuous measurements. You might also think a principal component analysis would be useful here as well. Look at your data graphically using various measures, those and maybe other ones, and then similar to what we did with the place-kicking data set, come up with an initial determination of, do you think that that we will be able to differentiate between the 3 different wheat types? Okay? Tell me what characteristics lead you to that conclusion. Also, pay close attention to observation number 31. The reason being is then explained in part B. So, this data is real data that I came across when I was doing some consulting. And this number 31, as you will find out, kind of looks weird. It's not a statistical term, but it looks weird in comparison to the other observations, okay? And I showed some of these plots that I generated to the subject matter researcher. I think he was in the Department of Grain Science. And he said, okay, that can't be right. That must be due to measurement error. And so because of that, we threw that observation out of the data set and continued with the analysis. So part B, I want you to show me how you throw that observation out of the data set so that you don't include it anymore. Show me how you did it. And then for the rest of the project, use this data set now that only has 275 observations remaining. Number 2. Now, similar to what we did with the place-kicking data set, you're going to be applying discriminant analysis to the remaining observations in the data set. First, you're going to use linear discriminant analysis. You're going to use cross-validation to get a measurement of how well the procedure is doing. You're also going to do something called priors proportional. That will be explained more next time. And then tell me, what were the percent correct classifications for healthy? Percent correct classifications for sprout, scab, and then overall. Also, give me a 3x3 classification table. So with place kicking, we saw 2x2 because we had 2 different possible populations. Here we have 3, so you have a 3x3 classification table. Then lastly, for part 2, in part B, you're going to see in the discriminant analysis homework for this section, I'm sure all of you have already looked at it, so this is not going to be new to you. You're going to see an interesting plot that looks like this. And what this does, this is for a particular homework problem where there's 2 variables, variable 1, variable 2 for the lack of a better name. It shows you which observations correspond to population 1 and population 2, and it shows you how they were classified. So, for example, let's focus on this one right here. The smaller plotting point is the original population. So in this case, for that particular observation, the original population is population 1. The larger point is the predicted classification. So this observation is predicted to be in population number 1. So we are correct for this particular observation. Let's actually look at this one. Oops. So in this case, the smaller plotting point is population 1, and you can see that I have a triangle over it, meaning that it was classified as population number 2. This is an error. So the nice thing about this plot is it shows you which observations you're getting correct and which ones you're getting wrong, and where the rights and the wrongs are occurring. I actually showed a plot like this to the grain science researcher that I was working with, and he thought it was really cool. Because it is. It's kind of a cool plot because it helps summarize everything. Now, in our case, though, oops, that. In our case, though, in our data set here, we have about 5 or 6 variables. So, can you do a plot like that exactly? No. But what you could do is find the principal components. Find the first 2 principal components, and now do a plot, just like what we saw. Okay? Sorry, we went a little bit long here, and I went through this a little bit more quicker than I wanted to. Next time, we'll probably finish the discriminant analysis section. If we don't, there will be only a little bit left to do. And I think this problem number 2 will make a lot more sense then, if it doesn't already. But if you have questions in the meantime, please feel free to post them to the listserv, and also come prepared to ask them during our next class. So that's it for today.